In this segment, I want to show how we can compile and run numerical expressions on a simple virtual machine. What we're going to do is produce a stack virtual machine. It simply has a stack which is manipulated by the machine instructions. So for example, the push n instruction pushes the integer n onto the top of the stack. So push 8, if you see the diagram, shows the stack before the operation and the stack after performing the operation, the instruction. So there's the push instruction, there is the fetch instruction, which fetches the value of a variable from an environment. So fetch a here, if the environment associates a with the number 4, will fetch that number and push it onto the stack. Add 2 takes the top 2 values on the stack, removes them and replaces them with the sum of those 2 values. And mul2 takes the top 2 values, removes them and replaces them with the multiplication of those 2 values. So those are the 4 operations. The machine just has a stack of numbers, and the operations have these effects on the stack. And just to show you that if we were to compile the expression 2 plus 3 times a, we would get this instruction sequence, and let's see what it does. If we push 2, we get 2 on the stack, then push 3 puts 3 on top, fetch a puts 4 on top, mul2 takes the top 2 elements and replaces them by their product, and add 2 takes the top 2 elements and replaces them by their sum. So we finish up with a stack that has one number on it, namely the value of the expression. So if we're to do all this in Haskell, we need to show how to model machine instructions, how to model the machine running, and how to compile an expression into a sequence of instructions. So we need to think about how we're going to represent these various things. And we can start off by defining some types. We can say, here's a type of instructions. Let's push this particular integer, fetch this particular character, and then the instruction add 2 and the instruction mul2. So we've got 4 kinds of instruction. A program then is a sequence of instructions. Let's represent that as a list. A stack is a sequence of integers. Let's again represent that as a list. So we've defined the types that we're going to be working with. We then need to think about how we define the programs that run over them. So we will have a program compile that takes an expression, sorry, a function, the functions that run over them. We'll have a function compile that takes an expression and returns a program. And we'll have a function run that takes a program and an environment and gives us an integer at the end, the result of that evaluation, that execution. Well, in fact, we'll do something else. We will have a define a function that takes 3 arguments, a program, an environment, and the state of the stack so far, and it will return an integer that results from running the program from that particular state. And we'll see how that's defined now. So suppose we have a program push n. The first thing in the program is push n. So we define this by pattern matching. We're saying the first thing in the first instruction is push n, and we have an environment env and a stack. What's the result of that? Well, it's another call to run. This is another example of tail recursion. So what do? The next step we get by running, we remove the push instruction. So we run the continuation in the same environment, but with a stack now that has n on the top of the stack. So that represents one step of the program, and then we run the remainder. In a similar, and we can see the result of push here. Just a reminder that that's how push behaves. So that corresponds exactly to how we said push behaved. In a similar way, fetch takes fetch of a variable will look up that value of the variable and place the value on the stack. So if we run the program whose first instruction is fetch, that has the effect of we then run the remainder of the program in the same environment but in a stack where there's that extra value on the top. What about running an add instruction? Well, we inspect the stack. There need to be two elements on the top. We remove those and replace them by their sum, and then run the remainder of the program. Again, you can see that's what's happening here. And finally, with multiplication, we will do the same thing. We'll take the top two elements off the stack and we will return a multiplication. Now, what's the final case? The final case is what happens when there is no more program to evaluate, to execute, and we assume that there is a number on the top of the stack. We return that number. So this is the way we run the stack machine. The first four clauses are tail recursion that explain how to do a single step in the recursion. So that we push by putting a number on the stack, we add by taking two numbers off and replacing them by their sum, and so on. So that shows how we can run the stack machine. So we've seen how the machine works, we've seen it in an example. The one thing that we still have to do is to explain how to compile. And here is the compilation. To compile a number, we simply push the number. To compile a variable, we simply fetch the variable. What do we do to perform an addition? The answer is we include all the code for the second sub-expression, because what that will do is put, when we execute it, when we run it, it should put the value of the second sub-expression on the stack. And then on top of that, we will get, as a result of compiling E1, the value of the first sub-expression. So after performing the instructions in compile E2 followed by compile E1, we should have added the value of the two sub-expressions to the top of the stack. So what we do finally then is we add the two together, and that's why, and replace those two by their sum, and that's what the add to instruction does. And in a similar way, multiplication works like that. So we put all the instructions for one sub-expression, which will put the first value on the stack, then the instructions for the second sub-expression, which put the second value on the stack, then finally we take those two off and replace them by their sum. So that gives us compilation. So we can see now we can compile and execute, and we can also directly evaluate. And you can see for the example program, at least, that those behave in exactly the same way. And you can try this out for yourself in the code that is referenced at the start of this masterclass, sequence of masterclass segments.